We have the graph of the velocity of a model rocket over time. You could see here that the velocity starts at 0. We're in feet per second. And the velocity is increasing. It is positive. So if we have a positive velocity, that means the rocket is going upward. Now, the velocity slows down, but it is still positive all the way up until t equals 8 seconds when the velocity becomes negative. So that means if we draw a graph of the height over here on the left, and we have time here, and this is height over here, or displacement, that means right up until t equals 8 seconds, the height is increasing. Now, first it's going to increase very fast, but then it's going to slow down, but still be increasing. But right here at t equals 8, the velocity is no longer positive. The velocity is 0. So that means the graph is flattening out here with respect to the displacement. So when it says at what time does the rocket reach its maximum height, the answer is at t equals 8 seconds. What is the velocity at that time? That is 0. Because after that, 0 in the upwards direction. Remember, velocity has direction. After t equals 8, you're going to see the velocity becomes negative. And when the velocity becomes negative, that means the height of the graph is going to be moving in a negative direction. Next, we are asked at what intervals is the acceleration positive. So let's go ahead and have an acceleration graph here to the right. And let's recall, very important, that the acceleration is the derivative of the velocity. So if we call the velocity the f function and the acceleration the f prime function, it's important to realize that the slope of the f function becomes the y value on the f prime function. So when we're asked this question, on what intervals is the acceleration positive? Basically, they're asking us at what intervals is the y value of the acceleration positive. Well, if the y value of the acceleration is positive, then by definition, the slope of the f graph is positive, meaning the slope of the velocity graph is positive. And when do we have a positive slope on any graph? When it is increasing. So here, this slope is positive. The velocity is increasing. This slope here is positive. The velocity is increasing. Therefore, the intervals where the acceleration is positive is going to be from t equals 0 to 2 inclusive union t equals, we're going to call this 11 to 13 inclusive. Next, we are asked, when is the acceleration constant? So let's draw our acceleration graph to the right and remind ourselves that the acceleration is the f prime graph when velocity is the f graph. So again, the y value on the acceleration graph is going to be equivalent to the slope on the f graph. All right, so this question asks us, when is the acceleration constant? When is the y value of the acceleration constant? Well, we move that same sentence over here. When is the slope constant on the velocity graph? And we could see that the slope is constant. This slope is a line. This is a line, which by definition is a constant slope between the interval when t equals 2 and t equals 11. So when is it constant? It's on this interval when t equals 2 to t equals 11. Now, part 2 of the question is, what is the acceleration? Okay, if they're asking us what is the acceleration, they're asking us what is the y value of the acceleration. What is the acceleration? This is time. Well, what is the acceleration? What is the y value is the same thing as saying what is the slope on the f graph. So all we have to do here, folks, is do a simple slope calculation using 2 points, and we're just going to do y2 minus y1 over x2 minus x1. This first point here is going to be 2 comma 90. I'm sorry, 2 comma 190, where the time is 2 and 190 is the velocity. And the point down here is time equals 11 and the velocity is negative 90. When we plug these numbers into this formula, we're going to get a slope of negative 280 over 9, or negative 31.1. So when they ask for the acceleration is going to be negative 31.1 feet squared per second. In question 4, we are asked to sketch a graph of the speed. Recall, this is the velocity. Folks, speed is a scalar quantity. It does not have direction. And speed can never be negative. Velocity here, we see, can be positive. Here it's above the line of y equals 0. So here, this is positive velocity, and then eventually we have negative velocity when the rocket starts falling down towards the ground. With speed, you can't have negative velocity. So folks, watch what we do here. We're going to copy the same exact graph when the velocity is positive. And then when we get to this point where the velocity starts to become negative, we're just going to take the absolute value of it. And taking the absolute value of it is simply going to reflect it right over the x-axis. So we're going to do a reflection of this portion of the graph where the velocity is negative. So we have this distance here is about, from the x-axis to this point here, is about negative 90. So we're going to go up to approximately positive 90 here. And instead of drawing a line that goes down as we move to the right on the x-axis, we're going to draw a line that moves up. And here we see that this portion of the velocity graph is concave down as it moves towards the x-axis. We're going to make our graph concave up as it moves towards the x-axis. Folks, it's very similar to what we do when we graph y equals x versus y equals the absolute value of x. Recall, the graph of y equals x looks like this. It's a very famous graph that goes 45 degrees angles upwards right through the origin. However, when you get to the absolute value of x, you can't have any negative y values. That always has to be positive. So what do? We reflect that over the x-axis, and you get your very famous v graph for the absolute value function. Next, our final question regarding this graph is number 5, when is the speed increasing? So here now, this is now a graph of the speed, okay, not the velocity. And recall, we took the graph of the velocity when it was negative and we reflected it over the x-axis. Folks, whenever you're asked about a graph where it is increasing, by definition, that means a positive slope. So a function is going to increase if and only if it has a positive slope. So where is this graph increasing? Where is the slope positive? Well, between the interval of x equals 0 and x equals 2. And again, we see it here. It's increasing at the interval where x is 8 to x equals 11. Next example, we are told that a particle moves along a line so that its position is given by this function. Folks, clearly, this is an upside down parabola. You see the negative, it has a coefficient of 1, which means it's not going to be wide, it's not going to be narrow, it's going to be perfect width. And I went ahead and drew it to save some time. I found negative b over 2a as the x-coordinate of the vertex, and then did f of 5 to get the y-coordinate. So, folks, when we're asked to find the velocity and we're given the position graph, two ways to think about this. The first is we know that velocity times time equals distance. Therefore, we're going to know that the velocity equals the distance over time. Now, if they want the average velocity between these two times, what we need to do is figure out what distance has transpired between t equals 0 and t equals 2. So, the change in position, we're negative 3 here. When we're at t equals 2, we're going to plug in 2 here to get our y-coordinate, and that will be the total distance that transpires over those 2 seconds. Now, folks, there's another way to think about this, and that is to remind ourselves that the velocity is the derivative of the position. So again, here's position, and here's velocity, and this is f, and that is f prime. So the y value of the velocity is going to be the slope on the f graph. So what we need to do, another way to do this, is to just get this slope here. So there's t equals 2, and if we can get the slope of that secant line, then that'll give us the average velocity over that interval. How do we get the slope of that secant line? Well, again, we do 2 comma f of 2, and here we know that if we plug in 0, we get negative 3. And when you do that, f of 2 turns out to be 13. And when you plug into the formula of y2 minus y1 over x2 minus x1, we get a slope of 8. So therefore, the average velocity in that interval is 8 feet per second. Now remember, when we're talking about the slope of a line, and they give us average, that means it's going to be between 2 points. Here, in the next question, they ask, find the instantaneous velocity at t equals 2. So this is a different problem. So we're going to do this by taking the derivative. Here, when you have an instantaneous velocity, there is no second point to do the y2 minus y1 formula. There is no secant line. Instead, you only have one point, and you have to find the slope there. Remember, the slope of the f graph gives you the y value of the f prime graph. So the slope right there, the instantaneous slope, can be found by taking the derivative and plugging in the value of 2. So the derivative of the original function here is going to be negative 2t plus 10, and we're going to go ahead and plug that right in, and when we do that, we get the instantaneous velocity is 6, therefore it is 6 feet per second, and that is the answer to this question. Folks, here is a summary of what we just did. We were asked to find the average velocity between the time t equals 0 and t equals 2. We went to our position graph. We plotted both of these points. We found s of 0 to be negative 3. That was right here. And then we found s of 2 to be positive 13. And then we drew a secant line, and we found the slope of that secant line. That's the way to do it. Now, here's what you might be tempted to do. You might be tempted to find the velocity at time t equals 0. Okay. And you might find the velocity at t equals 2. And you're going to be tempted to take the average of those two numbers. Folks, you can't do that. It works in this scenario, but that's only because the acceleration is constant. Okay, so let's go through that. If you're tempted to do t equals 0 into the velocity equation, into the first derivative, you're going to get a velocity of 10 at t equals 0. And then if you plug in 2, you're going to get 10 minus 4, or 6. If you add those together, you're going to get 8, which is the same answer that we got doing it the right way. But folks, that's only because this is a constant acceleration problem. This is the definition of constant acceleration. It's a parabola problem. There's constant negative gravity on that particle. However, in a few moments, later on in this video, we are going to have a function where the particle's motion is modeled by a cubic formula. Okay, something like this. Now, when you take the second derivative of that, okay, so s prime of t is going to equal 3t squared minus 18t. And when you take the second derivative of that, you're going to get 6t minus 18. This is not a constant acceleration because t is in the second derivative. So when your acceleration changes as you move from one point to another, you will not get this correspondence. So you cannot get into the habit of doing this. You have to do it the right way. You have to get the initial point, the second point, and take the secant line and the slope thereof. Next, we are told that a rock is thrown vertically upward from the surface of the moon at a velocity of 48 meters per second and reaches a height that is simulated by this function here in t seconds. Now, folks, first thing I'm going to do is I'm going to rewrite this quadratic equation in a manner that we're used to seeing it, and that's with the quadratic term first. So we got negative 0.8 t squared plus 48t. So we know this is going to be an upside down parabola. It's going to be a little bit wide because that coefficient is less than 1. So let's just do a quick sketch of this. We know that the fact that t is in both terms means that when we plug in t equals 0, we're going to get 0, which means that this rock is being thrown from the surface at a height of 0. So then this rock is going to go up and it's going to come down. Here is going to be our vertex, the x-coordinate of the vertex. When we do negative b over 2a, we're going to get x equals 30, or t equals 30, and if we do f of 30, we're going to find that this is going to be a height of 720. Okay, the next thing I want to do is immediately let's take s prime and s double prime. So s prime is going to be the velocity, and that is going to be negative 1.6t plus 48, and s double prime is going to equal negative 1.6. So again, when you get a constant acceleration, you are usually dealing with gravity. Okay, so what do we notice? We notice that the initial velocity, they gave it to us at that it was 48, but we really didn't need for them to give it to us. Because if we plug in t equals 0 into our velocity equation, we would have gotten positive 48. So let's see what they want to know. Find the rock's velocity as functions of time. Okay, we've done that by taking the derivative. How long did it take for the rock to reach its highest point? Well, we don't have to use calculus here. We could see that in 30 seconds we reached our vertex. But if you did want to use calculus here, what you would do is say to yourself, well, at its highest point, its velocity is 0. Here, it is not rising, it is not falling, you have a velocity of 0. So what we can do is set velocity equal to 0 and solve for t. So when you do that, you will find that t equals 30. Okay, next they ask, how high did the rock go? Well, we just do f of 30. We already did that at the very beginning. We got 720. How long until the rock hits the ground? Okay, two ways to do that. Non-calculus would be recognize that x equals 30 is also the axis of symmetry. Therefore, if this is 30, this will be 30. So it will hit the ground at t equals 60. The other way to do it is to recognize that on the ground, the height is 0. So you can go ahead and set the s equation equal to 0. So it would be negative, our original function, negative 0.8 t squared plus 48t. We're going to set that equal to a height of 0. And when we solve for t, we're going to pull out a t. And we're going to, we'll pull out a negative t, and we're going to get 0.8t minus 48 equals 0. We're going to use the zero product property and recognize that this function will be 0 when t equals 0, and when we set that factor equal to 0, and when we solve, we will get 60. Okay, next they ask, what is the acceleration due to gravity on the moon? And we already did that at the very beginning, and that would be negative 1.6. In this next problem, we are given the equation that follows a particle along a line at any position where time is greater than or equal to 0. So folks, if we look at this function, again, this is the position function, we see it's a polynomial. So our graph is going to do something like this. Okay, I don't know what this graph looks like, but let's just say it does something like that. Okay, what we can tell is the end behavior actually, because that's a cubic function, that's an odd function with a positive coefficient. So that means it's going to model the end behavior of this famous equation with an odd exponent and a positive coefficient. So it's just like this graph, which is down up, this is going to be down up end behavior. Okay, so they give us that function and they say, when does the particle change direction? So if this is the displacement function, okay, over time, that means here the displacement is in a positive direction, the height is increasing, that means our slope is positive. Here we see our slope is negative, our height is decreasing, so this point right there is where it changes direction. Okay, then we see another change in direction. We see that the slope is positive here. So the key is to identify these locations. Now, what do we notice about these locations? What is the slope right at this local extrema, this local maximum? What is the slope at this local extrema, this local minimum? In both circumstances, the slope equals 0. Okay, so we are looking for the time where the slope equals 0. Let's go ahead now and recall that if our f graph is position, then our f prime graph is velocity. Recall that the slope on the f function correlates with the y value on the velocity function. So where is the slope 0 is the same as saying where is the velocity 0. So what we're going to do is get an equation for the velocity. That's going to be s prime of t. That equals the velocity of t. We're going to take the derivative. We're going to get 3t squared minus 18t plus 24. And then we're going to set that equal to 0. And that's going to tell us where the velocity is 0. Okay, so when we do that, we could factor out a 3, fortunately. We're going to get t squared minus 6t plus 8 equals 0. And then we could further factor this to t minus 2 and t plus 4 equals 0. Therefore, at t equals 2, that should be a minus. At t equals 2 and at t equals 4, we are going to have a zero velocity. Now, folks, we're not done yet. Here's why we're not done. Because it's possible to have a slope of 0 on this graph, but not have a change in direction. What do I mean by that? Look at this very famous graph. Okay, this is y equals x to the third power. All right. Y equals x to the third power has a slope of 0 right here, but this is not a local extrema. If we put parentheses around that, that point in the middle is not higher or lower than the immediate points. The proof is that if we do y prime, we get 3x squared. 3x squared is the velocity function. It's the derivative of the original function, which means it's the slope of the original function. And look, our slope is always positive. This graph never changes direction. So how are we going to approach this now? We have two potential locations. So what we need to do now, folks, is confirm as to whether or not those two t values are indeed local extrema, or do we have a situation like this where you have a zero slope but is not changing direction. Okay, so what we can do here is we're going to do a sign analysis of the first derivative. So here's our first derivative right there. We do not need to include the 3 because it does not change the sign. Any positive component, any positive factor is not going to change the sign when you do a sign analysis. So let's go ahead and put the rest of the first derivative, which is here, and do a sign analysis. We're going to look at 3 zones. We're going to look at zone 1, zone 2, and zone 3. In zone 2, we're going to use 0 to plug in. In zone 1, we're going to use 0 to plug in. In zone 2, we're going to use 3 to plug in. And in zone 3, we're going to use 10 to plug in. If we plug in 0, you put your thumb over the t, you get a negative times a negative, that's a positive right there. Here, if you plug in t equals 3, that's positive, that's negative, for a total of negative. And if you put 10 here, that's positive, and you get a positive. So here's what's happening. If the velocity is positive here, which we proved in this area, if the velocity is positive, that means the slope of the graph is positive here. When you hit 2, the velocity is negative. That means the slope on the f graph is negative. When you hit 4, the velocity is positive. That means this slope is positive. So you do, in fact, have local extrema. The graph goes from increasing and decreasing. I'm talking about this graph now, the f graph. The graph goes from increasing, because it has a positive slope, to decreasing. That's a change in direction. Then it goes from decreasing to increasing. That's a change in direction. Okay, folks, just for completeness sake, there's another way to check these critical points. Once you get the critical points of the first derivative, the other option is to go ahead and take the second derivative and do the second derivative test. So if we take s double prime, that's going to equal 6t minus 18. Then what we do is we plug these critical numbers in the second derivative. We do not do a sign analysis of the second derivative. We simply do s double prime of the critical numbers. All right, and if they come out to be non-zero, they will be helpful. So if we plug in 2 into the second derivative, we get a negative value. That means our graph is going to be concave down in that area, and therefore you will have a local maximum. When you plug in 4 into the second derivative, you're going to get a positive value. That means the graph is concave up, and that critical point is going to be a local minimum. So we could say with certainty that the graph will change direction at t equals 2 and t equals 4. So, describe its motion. Well, we know that the particle is going to be increasing till it hits 2. How do we know that? Because we have a positive slope there. Then the particle is going to be coming down, and when it hits t equals 4, it's going to go up again. And again, we know our end behavior from the analysis that we did at the very outset. What is the acceleration of the particle at t equals 3? Well, we're simply going to plug that in. We're going to do s double prime of 3 because s double prime is our acceleration. And when we plug in at 3 into our acceleration equation, we get 0. Returning to this same function, we have two more questions. They asked, what is the displacement of the particle from t equals 0 to t equals 2? So here, we're going to find out what the displacement is at t equals 0. We're going to plug in 0 for t. We're going to put our thumb on all of these terms. Therefore, it's going to be 0. So one point is going to be 0, 0. And then, when t equals 2, we're going to do s of 2. And when we plug in 2 into this function, we are going to get 20. So therefore, we're going to go from 0, 0 to 2, 20, and our displacement is going to be the difference in those two y values, big minus small, is going to be 20. Next, they ask for the average velocity. Folks, here is the pitfall. You cannot take the derivative. Okay, let's do that. Let's do what we're not allowed to do. We're going to take s prime. Okay, I'm going to do a different color, red, so you know you can't do this. So we're going to take s prime of t. Okay, that's going to be 3t squared minus 18t plus 24. Now, we cannot take the velocity at 0, okay, which would be 24. Okay, if we plug in, if we do s prime of 0, we're going to get 24. And then if we do s prime of 2, okay, s prime of 2, we're going to get 3 times 4 is 12, minus 2 times 18 is 36, plus 24. That's going to be 0. What we cannot do is take the average of these two, the velocity at the beginning, the velocity at the end, and call that the average velocity. We cannot add these two and divide by 2. We get 12. As we'll see in a moment, that's going to be the wrong answer. The right way to do this is to create a secant line between these 2 points on the displacement graph. All right, so here we go. We're going to have a displacement graph here with 2 points. We're going to have 0, 0, and then we're going to have 2, 20. Okay, we don't know what this graph looks like. It does something like this. We don't know. But we do know that these are 2 points. We can create a secant line, and the slope of that secant line is going to be the average velocity between the 2 points. So what we're going to do is we're going to do y2 minus y1 over x2 minus x1. And when we do that, we're going to do 20 minus 0 over 2 minus 0 equals 20 over 2 equals 10. That's the correct average velocity, not 12. Can't do it that way. And folks, that's because the acceleration in this problem is not constant. When we take the second derivative, when we get the derivative of the acceleration, you still have a t in there. Let's do it down here really quickly. So we have s prime of t is 3t squared minus 18t plus 24. That's s prime. And when we do s double prime, we're going to get 6t minus 18. That is not a constant acceleration. This acceleration is going to change as t changes. And in that scenario, these two will not match up.